This is video assignment number 4, springs. So what do we want to use springs for? There's 3 main topics. They are to exert a force, to provide flexibility, and to store energy or absorb energy. So how are we going to determine exactly how successful a spring is at exerting a force, providing flexibility, or storing/absorbing an energy? Well, we're going to use the 4 main design components of springs, which are stress. So under stress, the main stresses we're going to be talking about is shear stress, and that's going to be torsional or direct shear. And then we're also going to have 2, which is deflection, so how much the spring moves when a force is applied. And this can be up and down, or side to side, or even rotate, I guess. Could rotate. Then we have stability, which we're going to use that to determine how long the spring should be. Because if we have too long of a spring, and we apply a force too long and too skinny of the spring, we apply a force and it's gonna, what in the, damn, I just peeled off something. Hey, that's not good. It's going to sort of come out like that. We don't want that. It's not good. Okay, and 4, we have the strength of the spring, which is going to mainly deal with, how small the wire is and the diameter of it and how much force it can handle. So we'll come back to talking about stress and how we calculate what values we calculate these for. First, we should probably cover the types of springs and the ends of springs, because based on what type of spring we have and the ends will determine certain tables we use to find values later. So we have 5 types of springs. The first one is the compression spring. So that is going to be a spring. It's pretty basic. You're just going to have something ground there, your spring, and another ground there, and the force will be applied like that so that the spring deflects downward, and you're going to end up with it being shorter than it was before. So this would be the deflection, which was one of our design parameters, was that. And then we have a tension spring. So that spring is going to be more open-ended. So let's say we have a hook here, spring, and then another hook. So usually force is going to be applied up and down. So this spring will get longer when the force is applied. And the deflection would be something like that. So 1, we have our compression. 2 is our tension spring. And that's only 2 of them. We got 5 in total. So the third one is going to be a torsion spring, which it can be a vertical or horizontal, but let's say we're just going to have a horizontal one because it's Jesus, I haven't had a horizontal example yet. And this spring is going to have more of a torsional force, as we've talked, and it's actually going to compress by rotating. So in this case, since the force is that way, then the spring will get a little shorter, and our deflection will be this and this distance, and we can add those together to determine the total deflection. The fourth one is a constant spring, which is a little stranger because it's a spring and its coil is all in one spot, and as a force is applied, let's say out this way, this is going to keep extending and this is going to unravel, so that if we had a graph of this and we showed the load, it's actually going to stay constant after it hits this point versus going something like that. And then finally, we have a variable resistance spring, which I don't really know what it looks like because I guess you could have a thicker diameter and stuff, but the graph, the load could look like this, you know, we apply a load and then it goes back down. So that'd be a graph of a variable spring, which, you know, the resistance changes as the compression changes. So now let's get back to now that we know about the 5 types of springs, we also have 4 types of spring ends, which is how the spring, if you know we have a compression spring, what this area and this area, what they're going to look like. So the 4 types that we have are open, not grounded. We have open grounded. We have closed, not grounded. I'm just going to draw G for grounded, and we have closed, grounded. So how are we going to use these? Later on again in the when we're determining out stress, deflection values, stability, and strength, we're going to have to use a chart for some of our variables, and you're going to use the type of spring, and then the ends are a big component of how we determine those values. So let's get into it. So we're going back to stress was our first main design component of the spring, and we said that the main one was going to be shear stress. So to determine stress, you're going to use this equation. This is the most basic form of this equation that changes as we figure more things out. Okay, so we got a lot of variables here that we don't know what they mean. Well, we can just assume that F is the force applied to the spring. And now we have big D and little d. So for this, we're going to draw out. So little d is going to be this distance right here of the coil, and that's going to be the wire diameter, and then big D is going to be this distance, which is the coil diameter. So if we had the coil diameter, wire diameter, the force, we could calculate the stress value. We also, from this, can find another thing we'll be able to use later, which is the spring index, which is just the coil diameter over the wire diameter. And sometimes we might just be given, if we're trying to make a spring, we might just be given what the spring index is and the coil diameter, and that's what we saw for the wire diameter, and vice versa, all over the place. So we also may have, though, a different force in the spring due to curvatures. And if we do have a curvature effect on the spring, we're going to have this new variable, KB, and that is going to equal, go back, and we're going to be using the spring index here again. And so that, we just plug that in front of the new, KB times this. And we also have a KS value, which is for stress correction, which is once again using the C values to C. So these are the main components you're going to want to use while calculating stresses in the wire, and they're going to be mainly focusing on shear stress. So the second one we have is deflection, which is a little bit simpler. So we talked earlier about the different types of deflection in the spring. If it's horizontal, you're going to have deflection could be this, how much it travels up, how much it travels down, vertical, how much it goes in and out, stuff like that. But for this, we're going to use another K. We're just using plain old K again, which is the deflection of the spring. So this is, I guess, K, not what I was using earlier. And that is going to be the wire diameter to the fourth times G, which will be given, or we'll have to solve using what type of wire it is, what type of steel or whatever we're using. And then that's all over 8 times the coil diameter cubed times NA. So NA is our new variable that we don't know about, and NA is actually going to be equal to the total number of turns that are active on the spring. So we have a couple of N values. We have the total number of active turns. We have NT, which is the total turns. And NT is usually found using a graph, or we can do it the other way, or using the charts, which again references closed end, grounded, closed end, not grounded, open and grounded. And we can solve for these either ways. If we get the total number of turns, we can go back, plug it in, and say, for example, I think for like 12 turns, NT is equal to NA plus 2, or closed-ended. For a closed grounded thing, it would be NA plus 2 is equal to NT. So that's pretty much it for deflection. You just determine deflection using your coil diameter, wire diameter, and the number of active turns, because the active turn number is how much of the spring is actually going to affect the force. So the third design parameter is going to be stability. And once again, stability is, if we have a wire or a spring that's too long, when we apply a force, it's just going to bend out like this instead of just collapsing or going straight down how we want it to. As you can see, we have movement this way, which we don't want. So for stability, the equation we're going to be using is for determining max spill. Yeah. So we're going to be L naught, which is the length, is less than pi times coil diameter over alpha times 2 and E minus G, which is given to us usually, over 2G plus E to the 1/2. So we know all this stuff, and we could use that to solve for the minimum length of the spring. And if the length is greater than this value, or maximum length of the spring, if it's greater than that value, then we have to somehow shrink the spring. And a common value for this would be, for example, in steel, L naught was less than 2.63 the coil diameter over alpha. So the final design parameter is strength. So this is, strength is determined by how small the wire diameter is. So we're going to be using the ultimate strength to determine this, which is A over dm. Once again, this is pretty simple. A and M are both found in tables that we use, the open-ended and stuff that we talked about earlier to determine. So all you're really going to want to know, all you're going to have to know outside of that is the coil diameter. So those are the four main things you need to know for designing a spring. And I'm going to give you some recommended design conditions now if you were to want to design your own spring. So typically this is the value you want for your spring index. It's got to be greater or equal to 4, less than or equal to 12. For the number of active turns, you're going to want greater than or equal to 3, but less than or equal to 15. So this other value, which I did not talk about, which is pretty much how much safety factor and stress we're going to want on actual springs. If we're going to go to the full stress value, the spring's not going to revert properly to its full thing. So we're pretty much going to want to work at, this is a correction of 0.15 or greater than or equal to 1. We're going to be working over that. And then for, you're going to have an NS which is greater or equal to 1.2. So these are some typical values you're going to want when designing your spring. You want them in between these greater than, less than, and stuff like that.